Welcome to the fascinating world of zoology. Today, we are going to explore the most successful group of animals on our planet, the arthropods. From the tiniest insects to massive crabs, we will uncover the biological secrets and mathematical rules that govern their incredible lives. Get ready to learn how their unique armor-plated bodies work. To understand arthropods, we must first imagine their unique way of living. Imagine wearing a rigid suit of full-body armor made of tough plastic. You can move easily thanks to flexible joints, but there is a catch. As you grow, the armor does not. To survive, you must periodically burst out of your old shell, stepping out completely soft and vulnerable, and wait for a new, larger suit to harden. This fascinating and terrifying lifestyle is the everyday reality for arthropods, the undisputed masters of the earth. Now that we have a feel for their armored lifestyle, let us look at their formal biological definition. The word arthropoda comes from Greek, meaning jointed foot. This refers to their jointed appendages, which act like complex levers for rapid movement. Their bodies are covered in a protective exoskeleton made of a tough carbohydrate called chitin. Furthermore, their bodies are segmented. Over evolutionary time, these segments have fused into specialized regions called tagmata, like a distinct head, thorax, and abdomen. Internally, they feature an open circulatory system where blood directly bathes the organs within a cavity called a hemocoel. With such a highly specialized body plan, it is no surprise that arthropods absolutely run the world we live in. They account for over 80% of all known living animal species. Their ecological impact is staggering. Without insects like bees, our agricultural crops would never be pollinated, leading to a collapse of the human food supply. In the oceans, crustaceans like krill form the foundational base of the food web, feeding massive blue whales. Meanwhile, terrestrial arthropods like spiders act as crucial pest controllers, keeping destructive insect populations in check and maintaining perfect balance in natural ecosystems. Because of their immense ecological success, we must understand how they physically develop. Because an arthropod is trapped inside that rigid exoskeleton, its growth can't be smooth and continuous like a human child. Instead, it must grow in sudden, discrete jumps through a shedding process called molting, or ecdysis. The specific stages of life between each molt are known as instars. In the early 20th century, scientists realized that this seemingly chaotic shedding process actually follows a strict, predictable mathematical pattern, allowing us to calculate exactly how an insect will grow over time. This predictable pattern brings us to a beautiful mathematical equation known as Dyer's law. Conceptually, this law states that the linear dimensions of an insect's hard parts increase by a constant ratio at each molt. In this formula, Wn represents the physical dimension, like head width, at a specific instar stage n. W0 is the initial size when the insect first hatches. The variable r is the constant growth ratio, typically between 1.2 and 1.4. Finally, n is the number of molts. If the growth ratio increases, the insect reaches a massive size much faster. Before we move on, let us see this formula in action with a concrete example. We are given a newly hatched caterpillar with an initial head capsule width of 2 millimeters. Biological measurements give us a constant growth ratio of 1.5 per molt. we need to find the head width at the third instar stage, meaning n equals 3. We substitute our known values into the exponential growth formula. First, we calculate 1.5 raised to the power of 3, which gives us a multiplier of 3.375. Multiplying this by our initial 2 millimeters gives us our final answer. The head capsule will be exactly 6.75 millimeters wide. Now that we have calculated how arthropods grow, we must ask a crucial question. Why do they stop growing? Another fascinating mathematical concept explains why we do not see giant, horse-sized spiders roaming the earth. The limitation comes down to the physics of scaling. Specifically, it is the relationship between an animal's total volume and the cross-sectional area of its legs. As any animal grows larger, its volume and mass increase much faster than the structural strength of its exoskeleton legs. This biological constraint prevents arthropods from reaching massive sizes on land. The physical limitation we just discussed is governed by a principle called the square-cube law. Conceptually, this law dictates how properties change as an object scales up. In these proportional relationships, m represents the total mass of the arthropod. A represents the cross-sectional area of the legs, which determines how much weight they can support. L represents the linear length of the animal. Because mass scales with the cube of the length, but leg strength only scales with the square of the length, a giant arthropod becomes incredibly heavy very quickly. If length increases, mass vastly outpaces the supporting area. Let us apply this square-cube law to a hypothetical scenario to see what happens. Imagine a normal ant that is 1 centimeter long, and we magically scale it up to be 100 times longer, making it 1 meter long. We need to determine how its body mass increases compared to its leg strength. We calculate the scaling factor for mass by cubing the length increase of 100, giving us 1 million. We calculate the scaling factor for leg strength by squaring the length increase, giving us 10,000. The final result shows a massive mismatch. The ant is 1 million times heavier, but its legs are only 10,000 times stronger. So we have calculated the multipliers for our giant ant. This brings us to the proof of why giant arthropods cannot exist. By comparing the two results, we set up a ratio of the mass multiplier to the strength multiplier. Dividing 1 million by 10,000 gives us 100. This mathematical step proves that the mass increased 100 times faster than the structural strength of the exoskeleton. The intuition here is clear. The legs simply cannot keep up with the body weight. Therefore, we have proven that the giant ant's legs would instantly snap under its own immense weight, restricting arthropods to small sizes on land. Having explored their physical constraints, let us now look at how biologists classify the immense diversity of arthropods. We begin with the first major subphylum, Trilobidomorpha. This group consists entirely of extinct marine arthropods known as trilobites. These ancient creatures dominated the oceans millions of years ago. They are characterized by a body divided into 3 distinct longitudinal lobes. Although they are no longer alive today, their abundant fossils are incredibly important. They provide us with crucial clues about the early evolution of jointed appendages and the ancestral body plans of all modern arthropods. Moving forward in evolutionary history, we encounter the second subphylum, Chelicerata. This group includes familiar animals like spiders, scorpions, ticks, and horseshoe crabs. The defining feature of this group is the complete absence of antennae, which is quite unique among arthropods. Instead, they possess specialized feeding appendages called chelicerae, which often take the form of venomous fangs or sharp pincers. Their bodies are typically divided into two main regions: a fused head and thorax, called a cephalothorax, and an abdomen. With 4 pairs of walking legs, chelicerates are highly efficient predators in both terrestrial and aquatic environments. From the venomous chelicerates, we dive into the water to meet the third subphylum, Crustacea. Encompassing crabs, lobsters, shrimp, and barnacles, these are primarily aquatic animals. Crustaceans are unique because they possess 2 pairs of antennae on their heads and have biramous appendages, meaning their legs actually branch into 2 distinct parts. Because they live in water, they typically have a hard exoskeleton, heavily reinforced with calcium carbonate, making it much heavier and stronger than the exoskeletons of terrestrial insects. They breathe using gills and play an absolutely vital role in aquatic ecosystems as both predators and prey. Finally, we reach the fourth and largest subphylum, Uniramia. This massive group brings together insects, centipedes, and millipedes. These animals are characterized by having uniramous appendages, meaning their legs are unbranched and end in a single tip. They possess a single pair of antennae and breathe through a highly efficient network of internal tubes called trachea, which deliver oxygen directly to their tissues. Most remarkably, the insects within this group are the only invertebrates to have ever evolved the ability to fly. This evolutionary breakthrough largely explains their unparalleled global success and diversity across the planet. To truly visualize what makes these creatures so successful, let us look at a generalized arthropod body plan. Here, you are seeing a classic insect model. Notice how the body is clearly divided into 3 distinct regions, or tegmata: the head, the thorax, and the abdomen. On the head, you can see the sensory antennae and compound eyes. Attached to the thorax are the defining jointed appendages, acting as complex levers for movement. Finally, observe the segmented nature of the abdomen, all encased within that tough, protective, chitinous exoskeleton. This modular body plan is the ultimate blueprint for evolutionary success. We have covered a tremendous amount of ground today, so let us summarize our key takeaways. First, the phylum Arthropoda represents the pinnacle of evolutionary success, defined by their jointed appendages, segmented bodies, and protective chitinous exoskeletons. Second, we learned that because their armor is rigid, they must grow through a mathematically predictable process of molting, while the physics of scaling prevents them from reaching massive sizes on land. Finally, by classifying them into subphyla like Chelicerata, Crustacea, and Uniramia, we see how variations in their body plans allowed them to conquer virtually every ecological niche. You now understand the core characteristics of the most diverse group of animals on Earth.